In this video, I would like to review how to read motion time graphs. Recall, when we are reading and analyzing motion time graphs, I want you to consider four aspects of these graphs. I want you to look at the slope, the area under, significance if the motion crosses the horizontal time axis, and any curvature in those graphs. And we're going to be looking at the position, velocity, and acceleration as a function of time graphs that we've been reading and analyzing in previous videos. So let's get started with this first section here. You can see that this object is moving off to the right in the positive direction with a constant velocity. We're going to also define our starting initial position, x naught, as 0 meters. You can see that it has a constant velocity because looking at the slope of a position time graph will give you the velocity, and that slope in those first 2 seconds is not changing. So in other words, the velocity is not changing. It is at a constant rate. Next, we can look at the slope of a velocity as a function of time graph to find the acceleration. Now, a cursory look at the graph there reveals that the slope is 0. And indeed, we have 0 acceleration occurring in that point. Lastly, the area under the velocity time graph will give you the displacement. So if you were to do base times height of this area here, you would get a displacement of positive 5 meters, which is exactly where the moving man ended up at the end of 2 seconds. Next, let's go ahead and look at this part of the graph where we have an immediate sudden stop. So the object or the moving man immediately stopped and remained stationary. So we have this little cusp here on the position time graph. We have this rapid deceleration as indicated by an extremely steep negative slope. And then, of course, I've addressed this in previous videos. We have this abrupt, almost infinite acceleration event. And because the object was moving to the right with a positive velocity, this negative acceleration is also a deceleration. And those are terms that I distinguish between in previous videos. The next segment here, we have the object abruptly moving in the negative direction. So again, we have a bit of a cusp here. We have the cross of the velocity time axis crossing the horizontal time axis. Significance of that is that at that instant, the object is moving backwards or in the negative direction. Okay? We also have this object moving past its original starting position. As defined earlier, x naught is equal to 0 meters. So the moving man has now gone to the left in the negative direction past his initial starting position. We also have, again, a negative acceleration occurring here, which means the acceleration in this case is in the negative direction, and the moving man at that instant moves off into the negative direction as well with a negative velocity. In the next segment here, we're going to look at the moving man's sudden stop. Okay, so velocity goes to 0. and the moving man is stationary. And that is occurring right here. Very abrupt, extremely steep slope here on the velocity time graph indicates an extreme acceleration event. In this case here, we have a positive acceleration. Moving man was moving in the negative direction, and an acceleration in the positive direction would lead to a deceleration here as well, which is exactly what occurred. And the moving man at this point is stationary. The moving man remains stationary before we get to this part of the motion time graphs. So, what is the significance of the curvature of a position time graph? The object is accelerating, and the object is moving in the positive direction uniformly. In other words, with a constant positive acceleration. And AP Physics 1 deals with uniformly accelerated motion. So we're dealing with a constant motion. Now, we can see curving in the position time graph, which means we have acceleration. We have a positive constant slope on our velocity time graph, and the slope of a velocity time graph is going to give us the acceleration. So the slope of the velocity time graph is constant and positive, and then we see our acceleration here is constant and positive as well. So our velocity and our acceleration vectors are positive to the right, whereas our position vector, the displacement, is negative because we defined our initial starting position at 0 meters. So at this point, the moving man is below the horizontal time axis. All right, moving on to the next segment here. We have curvature on our position time graph. We have a cusp here on our velocity time graph, and we have a deceleration now that immediately crosses the horizontal time axis, and that is indicative of a negative acceleration. So we have curving on a position time graph, which means there's some form of acceleration. In contrast to the last segment, we actually now have a negative slope, and we are now above the horizontal time axis. And the significance of that for a velocity time graph means we must be moving forward. So many students will see this negative slope and say, oh, the object's moving in the opposite direction. And that's not the case. That's a misconception. The object is moving in the positive direction because the motion is above the horizontal time axis. However, the object now is slowing down or decelerating. And we see this occurring here because it's moving forward, because the velocity is positive. We're going to now see a deceleration. And that, in this instance, a negative acceleration is a deceleration. So our vector directions for both velocity and position are now positive, whereas the acceleration vector is negative. And again, it is constant or uniform. Then we move on to this small section here that I would like to address, where we have the object is stopping just for an instant. And I know that because the velocity time graph, it's crossing the horizontal time axis. So the significance of that is that this object, if it's crossing that horizontal time axis, is stopped, even if it's for an instant in the process of changing direction, which is exactly what is occurring around 12 seconds. We have this abrupt change in the acceleration, And now we're going to see a change in motion as the object stops. And in this portion of the graph, the object is now moving in the negative direction. Okay, so it was moving to the right, it stopped because now it's moving to the left, which is our negative direction. And it has a constant velocity. We can tell by looking at the position time graph, has a constant negative slope. We can then look at the velocity time graph and see it is indeed constant and negative. And if velocity is not changing, then we do not have acceleration. And we can see this as well on the acceleration time graph, that the acceleration is indeed 0. Now, I want to distinguish one last time between the ideas of instantaneous and constant velocity and acceleration. So if I were to find the slope anywhere along this position time graph, anywhere in here, I could find the average velocity between t equals 12 seconds and t equals, say, 16.5 seconds, somewhere in there. I can find the average velocity. And in this case here, the average velocity would be the same as the instantaneous velocity at a given point on the graph. So at a given point, let's do 14 seconds. What is the object's instantaneous velocity? Well, just find the slope there. Find the rise over the run as we've been doing. And it doesn't matter where you do it along that segment, the slope is constant. So in this case, again, they are the same. So instantaneous velocity and acceleration refers to those vector quantities at one given instance in time, whereas average is over a period of time. And sometimes those quantities can be the same, as was the case in this example I just explained. So we have our object crossing now into a negative displacement, because at t equals 16 seconds, we see it's moving to the left of its original starting place. It's crossing the horizontal time axis, and we define the starting position x naught at 0 meters. Then we have this segment here as we get to the end of our motion. What's occurring here? Well, the object suddenly decelerates. It's moving to the left, then it stops. If it's moving to the left in the negative direction and it slows abruptly to a stop, then that means the direction of the acceleration must be positive. And again, it's an extreme acceleration event. It's off the chart here. And we see the object's velocity very suddenly goes to 0. So v equals 0 at this moment here, and it has stopped. So again, moving to the left, but it stops. If it stops, the vector is positive and to the right for acceleration, leading to a change in velocity from a negative value to a final velocity of 0 in the end of this graph. So we have, at this instant, the position is negative, the velocity is negative at that instant. This is a bit misleading here because this is right after this highlighted event. So I will now put negative velocity here to make sure you are not confused. At that moment, we have a negative velocity. An instant later, the velocity is 0. And again, we have a positive acceleration, which is leading to a deceleration. So a positive acceleration is a deceleration in this instance, in contrast to some earlier motion we studied in this video. And in the last segment, we have the object is stopped and remains stationary, which means we have a final position that is negative. we have a velocity equal to 0. And if velocity is equal to 0, that means acceleration is equal to 0. And we have covered now how to read and analyze motion time graphs. And in this final video, I've gone through the position as a function of time, velocity, and acceleration as a function of time graphs, and related all of those with the 4 aspects I've urged you to consider throughout: significance of the slope, significance of the area under, what is occurring when the motion crosses the horizontal time axis, and lastly, what is the significance of any curvature on these graphs. And I'll see you guys in class.